Hi everyone. In this problem, we actually don't run into a volume. This is going to be more two-dimensional. So we have somebody standing at the end of a pier. So let's just say this is our pier. Here's some fantastic art for you. And they're 12 feet above the water. And, I should be careful. 12 feet above the water, and they're pulling in a rope attached to a rowboat at the water line at a rate of 6 feet of rope per minute. How fast is the boat moving in the water when it's 16 feet from the pier? Okay, so I think I was okay to label the 12 feet. The height of the pier doesn't appear to be changing in this problem. So I'm going to draw this. Here's water level, and here's the boat. Yay, so pretty. Okay. Okay, so let's see here. 12 feet, pulling in the rope. Okay, so we're pulling in the rope at a rate of 6 feet per minute. So this 6 feet per minute, just looking at units, that's the rate of change of length. And in fact, it's the rate of change of the length of the rope. So I'm going to call this R for rope. And it absolutely should get a variable name because its length is changing. This is the rate at which it's changing, so I'm going to call that a dr/dt. And then once again, you want to try to be careful about this. The rope is not getting 6 feet per minute longer, it's getting shorter, so it should be negative. The length of the rope is decreasing. And that's what R means, length of rope. Okay, we want to know how fast the boat is moving in the water when it's 16 feet from the pier. So this can actually be a little bit tricky for people. How do we represent how fast the boat is moving? Although I don't know if people always recognize that it's tricky. We can just give it a name, right? We could say this is dB dt, but then you have to be really clear about what B means in this problem. So we're looking for dB dt. If you ever want to look at how fast something is going, you need to measure the rate of change of its distance from some fixed point. So basically we need to pick some fixed point in this problem, something that's not moving, and measure how far away the boat is. My pick here would be the pier. Horizontal distance to the pier we'll call B. So this is the distance from boat to pier. I guess we didn't need to write it because we've labeled it in the picture. So we're looking for that when the boat is 16 feet away, so when B is 16. Okay, so now we've got a picture, we've got everything labeled. We need a formula that relates R to B. And again, if you've made a good picture, hopefully you'll spot these. What I'm seeing is there is a triangle, not two triangles. Last time I had two triangles, which means I needed some similar triangles, but just a single triangle. And I think it's fair to say that it's basically a right triangle. We have a vertical pier, and then the water level is roughly horizontal, I would think. So what I want here is actually a Pythagorean theorem. So I'm going to say that R squared is equal to B squared plus 12 squared, which is 144. And that's my formula that relates R to B, that's it. So at this point you have two choices. One is just go for it, take the derivative with respect to time. The other is, since we are looking for a dB dt, you could solve for B up front if you want to. So it's up to you. I'm going to go for it with just taking the derivative. If I take the derivative of this whole thing with respect to t, I'm going to get a 2r dr dt, always thinking about that r as a function. This is an r of t. And then the same thing with b's. B is a function of t, so the derivative of my function squared is going to be 2 times my function times the derivative of my function. And then the derivative of 144 is going to be 0, so that's gone. I see right away, so I'm just going to go for it, that the 2's are going to cancel. So if you divide both sides by 2, they're gone. We know dr dt is -6. We know that B is 16. We're looking for dB dt. So right now, my trouble is that I don't know the value of R, and if I'm going to find dB dt, I need to. The good news is, back to our original formula, we have a really nice formula that given a B value could tell us an R value or vice versa. So while we don't want to plug in the 16 here when we're before we take the derivative, we can go off and do a little bit of side work and say, okay, so let's look at that like freeze frame, that instant in time when this is 16, and figure out what R is. So now we'd say R squared is 16 squared, I think it's 196, plus 144, which means R is going to be the square root of 196, 296, why can't I add 44 and 96, 340, oh my goodness, hold on, 96 and 44. Yeah, I think so. Okay, so back down to our work here, we can use that now that we've taken the derivative and captured this rate of change business. Oh, I know what I'm doing wrong and why that seems weird. It's because 16 squared is not 196. 16 squared, I think, is 256. Okay, so 256, so now, yeah, that sounds more familiar. Now I'm getting the square root of 400. I thought I remembered this working out nicely. The square root of 400 is 20, so let me come back over here and cross out this mess I was making. There you go. Uh-oh, here, I'll zoom up just a little. I wrote too far to both sides. Okay, so here. We have negative 120, and we need to divide that by 16, and that should give us our dB dt. So we're going to get a negative. What can I knock out of that? I could at least knock out a 4, 30, and then I could knock out another 2, 15, negative 15 halves, which is 7.5, is our dB dt. So we were asked, how fast is the boat moving in the water? I don't think we need to include the negative information. The negative is saying the distance from the boat to the pier is decreasing, but that's not really what the question is about. It was just how fast is it going? So my answer would just be 7.5 feet per minute. This is a really slow process. All right, thanks for watching.